Hi everyone, we're going to tackle questions 4, 7, 9, and 10 in these video solutions. If you hear any background noise, it's my good friend, Mr. Karlovsky. All right, here we go, number 4. The weather in Columbus is either good, indifferent, or bad on any given day. If the weather is good today, there's a 60% chance the weather will be good tomorrow, 30% it'll be indifferent, and 10% it'll be bad. If the weather is indifferent today, it will be good tomorrow with a probability of 0.4, indifferent, blah, blah, blah. We'll figure this out in the matrix. And then finally, if the weather is bad, it gives the same. Okay, so what is the stochastic matrix for this situation? All right, so we're going to just kind of use the from and to model that we were doing in class last time. So it's going to be from either good, I'll put them in what order here, good, indifferent, or bad, and then to good, indifferent, and bad. This could all be reflected in a matrix equation as well, but we'll just do it with setting it up with the columns and rows. Okay, so if the weather is good, there's a 60% chance it'll be good tomorrow. So G to G is 0.6. 30% chance it will be indifferent tomorrow. So G to indifferent is 30. And then G to bad is 10. Okay, for indifferent, it will be good tomorrow with a probability of 0.4. So indifferent to good is 0.4. And indifferent with a probability of 0.3. Which leaves us with 0.3 of indifferent to bad. And if it's bad today, it will be good tomorrow with a probability of 0.4, and indifferent with a probability of 0.5, and that leaves us with 0.1 for bad again. So that's our stochastic matrix. B, suppose there's a 50% chance of good weather today and a 50% chance of indifferent weather. What are the chances of bad weather tomorrow? Okay, so all that we have to do for part B is take our matrix M and multiply it by the probability vector 0.5 in the good spot, 0.5 in the indifferent spot, and 0 in the bad spot. That'll get us our probability for each of the 3 cases the following day. So let's do that on the calculator. Okay, so our 3 by 3 is 0.6, 0.4, 0.4. Sorry. And 0.3, 3.5, and 0.1, 0.3, and 0.1. Multiply the state vector 0.5, 0.5, 0. This gets us a vector that is 0.5, 0.3, and 0.2. So this is the probability of what's going to happen the following day. So our answer can be pasted in right there. Okay, so what does this tell us? That there's a 50% chance of the weather being good the next day, a 30% chance of it being indifferent, and a 20% chance of it being bad. C, suppose the predicted weather for Monday is 40% indifferent and 60% bad. What are the chances for good weather on Wednesday? Okay, so for part C, we're going to take 2 copies of M times M, because we're going from Monday to Wednesday. And the initial state vector this time is 0% for good, 40% for indifferent, and 60% for bad. And then we'll figure out what the state vector is, but they're actually only asking for what are the chances for good weather on Wednesday. Okay, so M squared times 0, 0.4, and 0.6. And that gives us this state vector. So our answer for the good would be there's a 48% chance of there being good weather on Wednesday. That's our good weather spot. Okay, 7. Find the steady state vector. Okay, so the only way that we know how to do this yet, although I'm going to teach you more soon, is to take this matrix and raise it to a large power. Usually 100 is sufficient. So if we take that matrix and raise it to the 100th power, that's going to get us a matrix full of the same column, and that same column is going to reveal what the steady state vector is. All right, so our steady state vector is 0.25, 0.5, and 0.25. You might think, before we get into class, you might think about what equation do we need to solve in order to actually formally find the steady state vector, think about what happens after continued applications of the stochastic matrix once you've reached the steady state vector. Think about how from state to state what's going on. We'll do that formally when we get to class. For 9, determine if P is a regular stochastic matrix. So I told you in the directions to go back a page and read the definition of that. So it says, we say that a stochastic matrix is regular if some matrix power, p to the k, contains only strictly positive entries. So we see that p itself does not contain strictly positive entries, but I'm going to define p and then start raising it to various powers to see if we can get only positive entries. All right, so p itself does not have only positive, but p squared does, and so that's pretty easy. P is regular in this case. So 9, let's say p is regular because p squared has strictly positive entries. Okay, and then we'll take a look at P for number 10. So this matrix has first vector 1, 0, and second vector 0.2, 0.8. So P itself does not have strictly positive entries. P squared doesn't either. P to the third doesn't either. P to the fourth doesn't. You can see what's happening here. That first vector stays as 1, 0 forever. That's never going to change. And so this means that P is not regular. Okay, so next class we're going to talk about how to find the steady state vector formally and why it is that when you raise P to a large power, you get the same column. You get the same vector in every column, which is actually the steady state vector. And if you have any more questions on these problems, I can answer them in class. Thank you.